where we're taking our stand-up science comedy trainings and our science communication trainings and moving those into a corporate sphere, where we can go to your company or we can go to your place of business and train people on how to communicate in a more upbeat, easier to understand way. We also do this. We have Georgia Science Junctions, climate survival trainings, or Jazz Hands, which is our science comedy shows. We'll be having our next science comedy show at TELUS September 13th. That's Jurassic Jokes, where we get to do copperlight jokes at the back end of a dinosaur skeleton. It'll be lots of fun. Tickets are still available for that on TELUS's website. Okay, and then our third pillar is going to the Georgia General Assembly and getting science into public policy. We go to the legislators and give them white papers, scientific background of the things that they are dealing with. So, because they're not going to be experts on a lot of the stuff that they're going to be making law on, we want to make sure they understand what the science says about that. One of the things we did recently, kind of in that front, is we just had our Environmental Justice and Climate Protection Conference, our third annual, down in Savannah, where we were talking to EJ communities around the state and of the issues that they are dealing with, trying to break down the silos so that you don't have very large groups like EPA or Sierra Club that can't get into communities because the communities don't trust them. And then we have small community groups that just don't have resources or funding. And so if we can combine those groups together, we can actually start getting things done. There's a lot of the stuff that I just said listed out in text. But thank you again to Manuel's for having us. I know we are a little early tonight for Science Junction. That's because Manuel's is very graciously letting us use the time because they have other things that's going on, DNC and whatnot. If you'd like to get involved with Science for Georgia, you can sign up here on this QR code. It'll go around later tonight. And you can get on the newsletter, check out our events calendar, or donate if you feel like it. We would really appreciate it. And now, Dr. Tamie Jovanelly. I'm going to give you a little intro right now. Dr. Tamie Jovanelly is an associate professor of research affiliate in geology at Berry College in Mount Berry, Georgia. She's received her PhD from Kent State University, her master's from the University of Nebraska, and her bachelor's from the University of Michigan. She is a Geological Society of America Fellow, a 2 times Fulbright Research Scholar, and a best-selling author. She'll tell you about her book later. And she's writing her second book now. She's also been a featured host on the Earth Unlocked for the Weather Channel. So you've seen her on TV. Additionally, following her passions for geology and teaching and travel, Dr. Jovanelly has created an educational tour company called Adventure Geology Tours, where she leads people to unique places to experience amazing landscapes. She just returned from one such thing in Iceland. So we have a lot of very nice things, also courtesy of her husband, to see. Here you go. Dr. Jovanelly.
Thank you. Thank you. Thank you for having me. I would be running for president myself, but I'm having way too much fun as a geologist. So maybe on the next slip. Again, my name is Dr. Tamie Jovanelly. I'm a geologist, a professor, an international researcher, and author. And last time I was at Science Tavern was in February of 2020. So it's been a few years since I've been here, but I'm really happy to be back. You look like a friendly audience. Before I get started, most people are interested as to how I ended up in Iceland in the first place. So my first trip to Iceland was in 2006 when I was setting up study abroad programs for Berry College Geology. And like most geologists, once you visit Iceland once, you're always looking for a reason to go back. So I've been to Iceland pretty much every year since 2006. And in doing that for more than a decade, I looked down at my notes and realized I had enough information to write a book. And so I did. I wrote an advanced geological concepts book for Wiley that was published in 2020. And the book is set up by focusing on tectonics, volcanics, and glacial features. And that's very much how I synthesized the island. When I was leading these study abroad trips, I would always come back, and the parents would be like, Dr. Joe, when are you taking us to Iceland? And so I got a great idea to set up a tour company. I launched it in 2019, and I've since expanded and rebranded to become Adventure Geology Tours. So we go, of course, to Iceland every year, but in addition, I take people to Cuba and Costa Rica, et cetera. And I take groups, and I also take individual travelers. So before we get started, there's one more thing that you need to know, and that is... Thank you, Google. That is, I don't speak Icelandic. As you heard, it's a pretty complicated Nordic language, and although I practice with really good intentions, I never quite nail it. So I'm going to apologize in advance for my mispronunciations. Additionally, because this is a talk on geology, you're going to see some acronyms on my slides. That includes MYO, meaning millions of years old, MYA, millions of years ago, and all of the drone footage that you're going to see within this talk is part of my personal collection. So it gives you a glimpse of this beautiful landscape that brings me back every single year. Because this is a talk on geology, we're going to start with some of the basics. So you're looking at a modern-day plate tectonic diagram, and we're going to locate ourselves in the great state of Georgia on the purple North American plate. And the North American plate, if we go up to the island of Iceland, it's sitting at approximately 66 degrees north. It is about 38 miles south of the Arctic Circle. It's bordered by the cold and dense waters of the Arctic Ocean to the north and the North Atlantic to its south. The island of Iceland is conveniently located on top of a divergent plate boundary. So you have that orange Eurasian plate moving or pulling apart from that purple North American plate. What else makes Iceland unique is that there is also a hot spot or a mantle plume. And that mantle plume is sitting just below the surface of Iceland. It's approximately 200 miles in diameter at modern day, and it's underneath Europe's largest remaining glacier, which is called Vatnajökull. And Vatnajökull currently takes up about 14% of the island of Iceland. It's approximately 5,000 square miles. So the history of Iceland is pretty unique in that it really results after the last Pangea cycle. So you have a supercontinent that begins to break apart and create something that we refer to as the mid-ocean ridge, which is at the bottom of the seafloor. And at about 50 million years, that hot spot is going to originate. That's called the Icelandic hot spot. And eventually that hot spot will breach the ocean floor at about 33 million years, producing layers upon layers of basalt that will eventually form the Icelandic basaltic plateau, which is the island of Iceland. So the oldest rocks on the perimeter of the island are only 33 million years old. So if we consider the age of the Earth to be 4.6 billion years, Iceland has barely had a birthday. And it is this divergent plate boundary that adds to the dynamics of this island. When we look at this map of Iceland, we find the Eurasian plate on the right and the North American plate on the left. And what we find is on this diagram, you see the red outline that represents the modern day divergent plate boundary. So when we look at the movement of these plates, we say that they are moving or spreading apart or diverging at a rate of 1 inch per year or 13 miles per million years. So when we say the island is being torn apart, it's being torn at approximately 1 inch per year or 13 miles per million years. And when you have pulling apart, you have extension cracks, and that also contributes to the volcanism that we see on the island of Iceland today, literally. So when we look at the island of Iceland, it's about the size of Virginia. yet there's 33 active volcanoes. I'll repeat that because that's your trivia question for tonight. Iceland, that's about the size of Virginia, has 33 active volcanoes. So pretty much anywhere you look in the landscape, you're going to find an active volcano, a dormant volcano, or some type of volcanic feature. When we talk about volcanoes in Iceland, we separate them into three major zones, whereby talking about the northern volcanic zone, the western volcanic zone, and the eastern volcanic zone. In the eastern volcanic zone, this is where our biggest and baddest volcanoes happen to be, is in the eastern volcanic zone, in Iceland and arguably in the world. When we look at modern day volcanism, we take ourselves to the Rani's Peninsula over here in the west, and we notice that we can take a look at the position of the volcanoes on this diagram that are labeled 1 through 33. And when we pay close attention, a pattern should begin to emerge. So the location of those 33 active volcanoes outline the position of where the divergent plate boundary actually is. And that makes sense, doesn't it? Because when you have pulling apart or spreading, you're creating a conduit for magma to more easily come up to the Earth's surface. So it's the divergence that allows for the magma to come more easily to the surface, and then you have the contribution of that magmatic hotspot. So the volcanism that we're seeing in the western volcanic zone on the Rani's Peninsula is referred to as a fissure eruption. But fissure eruptions are different than our textbook example of a conical volcano where you might see on CNN. So maybe like a Mount Pinatubo eruption. These fissure eruptions are very different. Why is that? Well, by definition, a fissure eruption occurs when linear underground passageways, called dikes, gets infilled with magma. And so what we can do is we can define fissure eruptions in two different scenarios. And I'm going to ask that you pay close attention to these diagrams because I'm going to be referring to them throughout the talk. So we have scenario 1 up at the top. And what we're looking at is a magma reservoir that is being infilled by the mantle. And that magma reservoir is just below a magma chamber that feeds a central volcano. And off of this magma chamber, you have a linear dike system. So in this situation, that's a fissure eruption that we refer to as scenario 1, we say that these fissure eruptions have predictability. And the reason why they have predictability is because in Iceland and in other places in the world, scientists have a really good understanding of the size and the shape and the volume of magma that can be held in that magma reservoir. So we have some idea of storage capacity. So we have an idea of how long that magma chamber will take to infill. And then when it's emptied, we have an idea of how long it will take to recharge. In addition, these linear dike systems in scenario 1 are relatively shallow. So they're really great for harnessing things like geothermal energy. In scenario 2, we would say that these are less predictable. You can have the presence or absence of a central volcano, but more importantly, when we look at the magma reservoir is being directly infilled from magma from the mantle. So you have the mantle that is feeding these linear dike systems. We say they're unpredictable because theoretically there's an unlimited supply of magma that's feeding this scenario too. In addition, they're much deeper below the surface, so they're harder to instrumentally monitor. So what I'd like us to do now is we're back looking at those position of where those 33 active volcanoes are. What we have established is that they neatly outline the position of where that divergent plate boundary is. But what I would like you to do is I would like you to focus on the red dots within this map. And when you focus on those red dots, those are going to represent scenario 1. Those are going to represent central volcanoes. But there's other areas on this map that are represented in light blue. Those light blue areas are going to represent scenario number 2. So when we tease out this diagram, what we find is that 14 of the 33 volcanically active areas in Iceland are designated as fissure swarms. So about half are scenario 1, where you have a central volcano, predictability. The other half are scenario 2, where they are become less predictable. And when we look at the Rainies Peninsula over here, where there's active volcanism, we notice that these are going to be scenario 2 type of fissure systems. When we talk about fissure systems, we like to monitor for them so that we can have clues as to when there might be an eruption. So to do that, the Iceland Meteorological Office collects some data, and they look for 2 specific characteristics. The Iceland Meteorological Office is equivalent to our United States Geological Survey. So they act as a clearinghouse for a variety of different types of data. Seismic data is one of those things. So what we're looking at here is a data set from a fissure eruption in Iceland that occurred on the Rainies Peninsula in 2023. On the x-axis, what you find is days, and on the y-axis, what you find is millimeters. When we look at this diagram, what we find is that the ground surface is flat, and then all of a sudden, we start to see a rise in the ground surface. We call that inflation. And that makes sense, doesn't it? So you have the magma that's upwelling from the mantle, and it's beginning to infill these empty dike systems, and so that magma begins to occupy space. And as it's occupying space, the ground surface is going to have to accommodate for that. And so it begins to rise. And so we can monitor that inflation. And then once the ground surface comes to its carrying capacity, it will essentially fracture or crack or fissure, and then it allows the magma to gently come to the surface. And when the magma chamber and the dike system is empty, eventually the ground surface will collapse and subside. And that's what you're seeing on the next diagram. So you're seeing a model where you have an elevated surface, and then you have your fissure eruption, and then your dike system and ground surface begins to collapse. So in looking at fissure eruptions, we can monitor for inflation as a precursor to an eruption, but we can also look for seismic activity. So this diagram of the Rainies Peninsula correlates to the data set that we just saw. And it's not so much about the energy of the earthquakes. So you might be familiar with the idea of magnitude of an event, where you have low magnitudes of 1 or much higher magnitudes going all the way up to 10, and that represents energy. The energy isn't as important here as how often these earthquakes are occurring prior to a fissure eruption. So when we look at this diagram, each of these individual dots represents an individual earthquake. They have very low level energy, a magnitude 1, a magnitude 2, a magnitude 3. But it's the sheer presence of all of these earthquakes that are happening prior to a fissure eruption. But you can have more than 10,000 earthquakes occur. And this makes sense too, because as the magma is infilling these linear dike systems, the ground around it is beginning to crack, and it gives off seismic energy, and that's what's being recorded. So prior to an eruption, we can measure the inflation, and then we can also measure the amount of earthquakes, and we look for those as indicators of an event to occur. So after the crack opens, you have this magma that will effusively come to the surface. So I've talked to some of you, and you're familiar with maybe like the Hawaiian Islands. The magma that we see on the Rainies Peninsula is similar to that. We say that it has a low viscosity or a low resistance to flow. And when this magma solidifies, it's going to solidify as basalt. We have samples coming around because this is a geology lecture. Sure. No. Yep, just that one. Patience. So when it solidifies as a basalt. So we would call these basaltic flows. What's fun to think about is that when the Vikings settled Iceland in 874 CE, they're seeing things very similar to what we're seeing today. So we have a historical connection to the Vikings. When the Vikings write about the fires on the Rhenish Peninsula, that's what they refer to them as. They refer to them as fires or curtains of fires. So when we look at the image on the screen, we have an understanding of exactly what we're seeing. In geology, we say the present is the key to the past, and the past is a key to the present. So the processes of fissure eruptions have been long-lasting. In addition, when we think about how Iceland is created, there's always been a hotspot. There's always been a divergent plate boundary. Therefore, there's always been volcanism on this island. The recurrence interval of volcanic activity is about 1 every 5 years. So every 5 years, there's some type of volcanic eruption on this island. So if you talk to an Icelandic person that's 100 years old, they've lived through 20 different volcanic episodes in their lifetime. So when we look at the readings of the early Vikings and their relationship to the volcanism, they're pretty nonchalant. The Vikings were pagans early. They moved later to Christianity, but they really weren't so much threatened by volcanism because they were nomadic. So if there was a problem in the landscape, they were very quick to up and move to another part of the pretty desolate island, thinking in terms of this too shall pass, and realizing that they have to work in cooperation with the landscape that they were living on. Sometimes these eruptions are considered to be tourist eruptions, and that's because they provide a little danger. You can get very close to a lot of these eruptions as long as you're in a direction that's away from the gases. My husband's very romantic. Romance isn't dead, folks. So you can see that we're in very close proximity to this particular lava flow, and we're in very low regard of danger. So sometimes they're considered to be tourist eruptions, and the Iceland Met Office encourages a lot of the times people to visit these because they are part of the natural beauty and landscape that makes Iceland unique. When fissure eruptions are described, we like to talk about vents or venting. This is a drone video from Bardabunga eruption in 2019, and what you're seeing is the formation of 2 different vents. Vents are localized areas along the fracture just where pressure has begun to build up. So you've got these localized bodies of magma where pressure is trying to escape the surface, and these are called vents. When we look at these vents, they're also sometimes referred to as spatter cones. So when you look closely, you can see these tiny, tiny pieces of magma going up into the atmosphere, and as they're cooling, they're falling down to the subsurface in tiny, tiny particulate matter. These are called tephra, and we have some examples. So around the top of the central vents, you have these tiny pieces that are called tephra, and that's very characteristic of vents and their formation. And the tephra will remain unconsolidated, so you can tell something about how old a fissure eruption is really by the amount of tephra that's still in place and hasn't eroded away. When we describe fissure eruptions, and usually in the media, they love to talk about the intensity and duration of a fissure eruption. This largely depends on if we're talking about scenario 1, where you have a central volcano and a magma chamber with a dike system off of that, or scenario 2, where you have deep-seated magma that's infilling these linear dike systems at some depth. So when we talk about intensity, we often talk about the fountain height of a fissure eruption. So the height of the magma that's coming off of one of these central vents. How high the magma is flowing is referred to the fountain height. We also like to talk about the discharge of the event. So that's usually reported in cubic feet per second. How quickly the magma is coming out of the fissure system and flowing on the Earth's surface. In addition, in terms of duration, this can vary wildly. So fissure eruptions can last on the order of a few days, a few weeks, a few years, a few decades, and even a century. So it largely depends upon how much and how quickly the magma is infilling these subsurface reservoirs. So what I would love to do now is I want to provide some context of the recent fissure eruptions by giving you some historical context. So I pulled out 3 really important historical fissure eruptions that have happened in Iceland that have been really well documented. The first one is referred to as the Mývatn fires. So we're going all the way back to 1724. This is 800 years after the Vikings originally settled the island. This particular Mývatn fires, and you might be familiar, is in the region of Mývatn, which is a pretty popular tourist destination. It's in the northern volcanic zone, and we're looking at these fires being associated with scenario 1. So the activation of a volcano that is called Krafla. And Krafla would be scenario 1. It's tied to a subsurface dike system. This is a pretty important eruption that was really well documented by a pastor who is living along the lakes of Lake Mývatn. And what he was especially reporting was how the lake basin was changing by the presence of this brand new magma that was coming to the surface. So about 18 square miles of this lake is going to be influenced. Lakes are pretty unusual in Iceland. You can have lakes along divergent plate boundaries where you have rift lakes, but you have very few basin lakes. And if they are present, they're in this fashion where they've been created by the presence of lava flowing at the surface and really creating a basin over time. So in the pastor, as he's documenting the Mývatn fires that lasted for 5 years, from 1724 to 1729, he's noticing that 4 different farmsteads are being overtaken by the Mývatn fires. If you visit this region of Mývatn, the pastor's house is still standing. So perhaps through prayer, but more likely through elevated topography, the pastor's house remains. So it's one of the oldest structures that you can visit in Iceland. So buckle your seatbelts because this is going to be a much bigger event. We're going to talk about the Lackey fires. They start in June of 1783. The Lackey fires are considered to be Iceland's worst natural disaster. The Lackey fires are considered to be Iceland's worst natural disaster. And that's saying a lot, right? Because what we said is that there's a volcanic event every 5 years in Iceland. But in the history books of Iceland schools, this is exactly what they write about. So when we talk about the Lackey fires, they are in the eastern volcanic zone. I told you that's where some of your biggest and baddest volcanoes are, even to this day. So they are associated with a volcano called Katla. And so, again, we're thinking in terms of scenario 1. But what makes Lackey fire so devastating is, imagine, June 1783, a crack in the Earth's surface opens up that's 15 miles in length. What? A crack in the Earth's surface opens up. It's 15 miles in length. In addition to that 15-mile fissure, you get 130 of these different vents that begin to form. The Lackey fires are only going to last 9 months, from June 1783 to February 1784. I love this picture. It's from Thor Thordarson. He wrote a fantastic paper about Lackey craters in 2003. I encourage you to take a look at it. So in this photograph, you can see the linearity of these crater rows in the eastern volcanic zone that were created in June of 1783. So what happens when you have 130 vents? You have a lot of magma coming to the surface to the tune of 42 billion tons. This is considered to be Iceland's second largest basalt flow in historic times. So what makes Lackey fires different than any other fissure eruption that we'll talk to tonight is its location. So we said that it occurs in the eastern volcanic zone related to the volcano called Katla, but more importantly, where this fissure is opening up is on the backside of Vatnajökull, Europe's largest remaining glacier. And so it's opening up in an area where there's glacial meltwater. So when you have magma intersect water, you end up with something that's called a phreatic eruption. And when you have a phreatic eruption, you can produce a lot of volcanic ash. And that's exactly what happened with the Lackey fires. The phreatic eruption produced enough volcanic ash to cover about 90% of the island of Iceland. So when we're looking at this map of Iceland, you see the orange. That's where all of this volcanic ash began to fall. Wait, there's more. This volcanic ash contained fluoride. It contained fluoride. And remember, what goes up, what comes down. So now you've got all this volcanic ash that's contaminated. It is going to fall into the crops. It is going to end up in the groundwater, and it's going to end up in the surface water. The cattle are going to be grazing on the crops. They're going to be drinking the surface water. The people are going to be eating the cattle, trying to eat the crops, but they're going to eventually be dissipated. They're going to drink the water. So the Lackey fires are considered to be among the worst natural disaster in Iceland, because what's going to happen by 1785 is that 1/5 of Iceland's population is going to perish from either fluorosis, from famine, or SO2 inhalation. Because when you have such a massive volcanic event, you're also producing a lot of volcanic gases. So we can think in terms of water vapor, carbon monoxide, carbon dioxide, and SO2. 1785, population of Iceland wasn't particularly big, so this was a huge hit to their island. But wait, there's more. So remember, what goes up has to fall down somewhere else. There is Europe, which is relatively nearby. Remembering this is before the internet, this is before cell phones. And what's going to happen is that the Europeans are going to be sitting, drinking tea, drinking coffee, drinking espresso, reading their newspapers, and they're going to notice an acid haze waft over their land. And that acid haze is going to bring 120 megatons of total sulfuric acid aerosol over the course of 10 episodes from 1783 to 1784. This is going to produce acid rain. The country is going to go into a famine. And it's even thought that things like the French Revolution could have resulted based on the Lackey fires. But wait, there's more. There's global consequences too. So, when we look at global data between 1783 and 1785, it has been documented that temperatures are going to decrease globally by about 4.8 degrees Fahrenheit. So this is a little bit counterintuitive. So when we think of volcanic gases, we think in terms of carbon monoxide, carbon dioxide, water vapor, SO2. We consider those to be greenhouse gases, those gases that warm our planet. But when you have 120 megaton of SO2 going up into the atmosphere, you can get this chemical exchange with water vapor to produce H2SO4, sulfuric acid. And sulfuric acid is an inhibitor for solar radiation. So from 1783 to 1785, you have this cover of the Earth that's prohibiting actually heat from coming into the surface. So when we look at data, as we can do in our backyard, global temperature is going to decrease by about 4.8 degrees. This is kind of a fun diagram for us to look at, where we have winter temperature records in the eastern United States. So on the x-axis, you have years, and on the y-axis, you have degrees Fahrenheit, temperature in degrees Fahrenheit. So for us in our backyard, this is the difference between having an average winter temperature of about 35 degrees versus having a winter temperature of 30 degrees. So it's a difference between a thaw and a freeze. And when we look at the global record, sometimes famine is also tied globally to the Lackey fires. So moving forward in time, I think it's also important to talk about a more recent event, and this is referred to as the Krafla fires. I've already introduced to you Krafla in the northern volcanic zone. So this same fissure system is going to erupt 250 years later after the Mevatin fires. This eruption is going to last 9 years. So from 1975 to September of 1984. And there's going to be 9 different rifting episodes. But what's unique about the Krafla fires is that the duration is on the order of days, only up to the longest eruption being just over 2 weeks. So the first eruption, December 17, 1975, 2 days, 3 days, 2 days. And then by the time we get to 1984, we see an event that's lasting 15 days. So very short duration events, but lasting for a very long period of time. Now, we learned an awful lot in the scientific community about fissure eruptions from the Krafla fires because they were slated to open a brand new geothermal plant in the northern volcanic zone in 1975. They were already ready to go. So they had built this facility and they were ready to turn on the switch. So in true Viking fashion, they decided, well, it's probably not going to stop. We're going to go ahead with our plans, right? This too shall pass. But they realized that they had to monitor a lot of the activity that was happening. So from the Krafla fires, this is where we learned about increases and decreases in ground surface, and we also learned about earthquake swarms being a precursor to fissure eruptions. So where we're at today is that there's been active volcanism on the Rainies Peninsula. And I'm going to show you the star represents the capital city of Reykjavik. And then we have a second star here that represents the city of Keflavik. Keflavik is where the international airport is. So if you fly into Iceland, you fly into Keflavik and you take a bus about 1 hour to the north to get you to the city of Reykjavik. When we look at the Rainies Peninsula, what you'll notice is that there are 6 independently named fissure swarms. And what you notice is that there's not any central volcanoes. So we're thinking in terms of scenario 2, where you have this deep-seated magma coming from the mantle and directly infilling these linear dike systems in the subsurface. The 6 fissure systems are in echelon to one another, and they're cross-cut by a divergent plate boundary. So the hash line represents the divergent plate boundary. And because you have that divergent plate boundary, you always have low-level earthquake events. I don't know that I've ever been to the capital city of Reykjavik where I haven't felt some type of earthquake, but they're usually a magnitude 4 or less. Now, the last time that the Rainies Peninsula was active was about 800 years ago, and that activity occurred in the Rainies Fissure, so the fissure that's furthest to the west. So the last eruption on the peninsula was about 800 years ago, and this produced the Rainies fires. And the Rainies fires happens from 1210 to 1240. So this fissure system was active for 30 years, and they produced something that's called Stamper Crater Row. And I like showing you this video because you've already seen how vents are formed. These are what vents look like when they become solidified. And so what we said was that around those central vents, you find tiny pieces of tephra, and that's what you're noticing around the flanks of these vents. Another thing that you notice is that they are completely linear features, and that makes sense now too. The Rainies fires, they weren't nearly as drastic as the Lackey fires. There's about 30 vents in total, but you can see how drastic the landscape had changed and how desolate the landscape is in this particular area. This is called Stamper Crater Row. So moving forward in time, our current fissure eruption, the most recent of those, began in 2021, and this occurred in the Fagradalsfjall fissure system. So remember that each of these act independently, and that's why they're named independently. And this eruption occurred in 2021. However, the Iceland Met Office was monitoring inflation and seismicity starting in 2019. The last time that this particular fissure was active was about 6,000 years prior. So this particular fissure had been dormant for 6,000 years prior to the activity that we began to see in 2021. When we talk about fissure eruptions, the location of the fissures is based on topography. And that's because there's usually not a city center that's very close. So when we look at the 2021 eruption that began to be active in March of 19, the fissure is opening in a location that's called Glendagalur, and over the course of 9 months, it will infill the valley and spread to an adjacent valley called Müller-Daller. So we're looking at a topographic map that represents, the purple represents where the lava flowed during this 9-month event. And on a topographic map, the areas that are, the lines that are closest together represent areas of highest topography. So we mentioned that sometimes these are referred to as a tourist eruption. This event in Fagradalsfjall was certainly considered a tourist eruption because it's 18 miles south of Reykjavik, and this area is largely uninhabited, and then the topography lent for areas of where you could get up high and look at the lava flow and be completely safe. So the Iceland Met Office encouraged people to visit this particular event. So over the course of 9 months, the lava field that's highlighted in purple spreads about 3 square miles. This particular event had 6 different vents. The colors on the screen now represent the thickness of the overall lava flow, with the cooler colors being thicker deposits and the lighter colors being thinner. So the areas that are purple represent an area that's about 400 feet in thickness. So really we're thinking about how this lava is filling up the valley. And there's 6 different vents that begin to form. I'm going to show you a drone video from this star, and it's going to show you the 2021 lava flow in this direction, so flying north. So you can have an understanding of truly how desolate it is. The black represents the 2021 lava flow and how it's solidified. You can see the upper topography because the lava is going to want to flow from high elevation to low elevation, and it's really going to meet the landscape where it is. Off in the distance, you can start to see one of those craters out here. So after that 9-month episode, the following summer, there was another reactivation of Fagradalsfjall just further to the north. My husband and I were lucky enough to be there. We were leading a group of an Association for Women Geoscientists, and so we were able to do the long and hard hike to get to this particular lava flow. It was only active for about a month. It had an initial flow rate of 1,100 cubic feet per second, and it's only going to cover half a square mile. And it only had 2 vents, and I'd like to show you this picture of one of those vents that were created because it gives you a close-up and slow motion view of how those tiny pieces of tephra begin to form as the magma goes up into the atmosphere and cools and falls back down to the surface. Almost exactly the following next summer, there was another reactivation of Fagradalsfjall, again further to the north. This eruption site is referred to as Little Her, which translates to Little Lamb in Icelandic, but again, it has to do with the topography. What's interesting about this particular eruption is that it had a really high flow rate at the end, 1,800 cubic feet per second. The lava is going to flow again from high gradient to low gradient, so this entire valley by the end of August 5th is going to be completely infilled with lava. We were lucky enough to visit this eruption site too. And so you're seeing the formation of a vent. And what I want to point out is most of these vents are asymmetrical, and that's because usually there's a breach. So you notice the breach in the lower left-hand corner. So you usually have one of those walls that begin to collapse. Off in the distance, you're noticing that some of the mosses have caught fire. And again, because this is a tourist eruption, we're upwind of the steam and the gases, which are always monitored by the Iceland Met Office. So you can kind of see how the valley is beginning to be infilled. You're noticing a lava river that has begun to form. And if you hike all that way, you might as well stay for the night show, because that's where the real magic is. When you're looking at lava flows, there's a temperature gradient based on color. So the lava that is gold, temperature is about 2,000 degrees Fahrenheit. Those that are darker red represent a temperature of about 1,000 degrees Fahrenheit. Some of you mentioned that you've been to Hawaii. Maybe you've been to a lava tube. This is exactly how a lava tube begins to form. So the darker basalt is cooled. The temperature of the lava is harder, and so it's able to erode a channel into that dark lava. The surface will cool first, and the surface will eventually form a cap. And then after the episode is over, the lava tube will be completely drained. You're noticing some what we call rafted basalt on the surface. Those form things like pohoi structures. So you can get these ropey types of textures that form on the surface and then eventually will solidify and become part of the geologic record. My husband's getting confident with the drone now. Don't worry, we have insurance and we've used it. So if you haven't been able to visit an active volcano, I highly recommend you do it. It's really a magical experience. You can imagine cold precipitation moving through the valley. When that cold precipitation hits the lava, it begins to sizzle. It kind of smells like charcoal. And then you occasionally get these waves of hot air coming off of the flanks of the volcano too. And of course, they're ever-changing and dynamic systems. So where we're at today is the volcanic activity and fissure system has moved to the adjacent Sarasingeti. So the activity has moved to the west to a different fissure system. Is Fagradalsfjall dormant? We don't know yet, but the activity has moved further to the west. Now, this is not considered to be a tourist eruption, and that's because there is a nearby city that's called Grindavik. And Grindavik is a fishing village. There's about 3,700 people that live in this town. So the Iceland Met Office and the government really wants to protect the city from looting, etc. And in addition, this area, because it's closer to the southern coastline, the topography is very flat. So there is little means to predict where the lava is going to go. In the Fagradalsfjall, it was in a valley, but here it's such low-lying topography, it's very hard to know the position of where that lava is going to flow. So when it opened up on December 18th of 2023, this initial event only lasted about a month, but the fissure was about 2.5 miles in length, and its proximity was only 1.86 miles north of the city of Grindavik. So the Iceland Met Office and the government was very quick to begin to build barriers, and they wanted to protect first a hydrothermal power plant. So there's a power plant near Grindavik that produces the water for Reykjavik. There's about 200,000 people that live in the capital city of Reykjavik. So they built the barrier for that first. Unfortunately, this particular episode did meet Grindavik before they could save about 4 houses. So after that initial eruption that occurred in December, the Iceland Met Office made some zoning maps, and they really honed in on things that they needed to start to protect. Not only did they need to start to protect the city of Grindavik, but they wanted to protect more the hydrothermal plant, and of course you're going to protect the Blue Lagoon, Iceland's #1 tourist destination, which is also near the city of Grindavik. So where we're at modern day is we are looking at months on the x-axis And we're looking at another inflation model whereby the ground surface is beginning to increase from bottom to top. So where we're at today is up here on August 20th. What the Iceland Met Office says is that another eruption is going to be imminent. Another eruption is going to be imminent. And so, again, for that reasons, the government and the Iceland Met Office are busy building barricade systems. My husband and I were just in Iceland in July, and we got to see some of these barricades. They're just using the basalt from the natural landscape, and they're piling it up anywhere from 20 to 30 foot high, with the idea that the barricades are going to help to redirect some of the lava flow. And sometimes they work, and sometimes they don't work. And so in the case of some of the road systems, they continue to be closed because they're having to reconstruct them as they go and try to manage these different types of eruptions. But the good news in all of this is a lot of really interesting geology data is being turned out. So the data from the 2021 Fagradalsfjall is just being analyzed and being published. Now, what we said was that Krafla fires were really important. They occurred from 1975 to 1984 over the course of 9 years. They told us a lot about inflation, deflation models, and seismicity, earthquake swarms. But remember, that was scenario number one in the terms of fissure eruptions dealing with a central volcano in a very shallow dike system. Here on the Rainies Peninsula, we're dealing with scenario 2, magma that's directly being infilled into these linear dike systems that are much deeper. So researchers have collected from Fagradalsfjall the molten magma, and they're looking at the specific geochemistry. So they're looking directly at the magma that's coming from the subsurface. And so what Bingman et al. Has published in 2022 is a paper that speaks to that. So on the top you have a cross-section from the eastern volcanic zone across to the western volcanic zone and across the Rainies Peninsula. And each of these letters represents those individual fissure swarms. So the F represents Fagradalsfjall. So when we look at this map on the bottom, it's showing you depth below the surface. And what Bingman is looking at is the geochemistry of this magma. And when they do that, what they find is that something that was suspected but had never been truly confirmed before. What they suspected is that the magma that's infilling these dike reservoirs are coming from at least 15 miles below the Earth's surface. You might be familiar with the term lithosphere. So you have the crust and the upper mantle that is separated by the Moho line, and then below the Moho line you have the asthenosphere. So this magma is coming from below the Moho line. So it's pretty exciting to confirm things that we've suspected. These are referred to as mid-ocean ridge basalt. And when they look at the geochemistry of the island or of the peninsula, the geochemistry is very similar. So it's suspected that this source of magma infilling these types of dikes have been around for the history of the island. Now, additionally, and concurrently, there's another group, Call et al. 2022, and they're also sampling Fagradalsfjall 2021 basalts. When you look at this basalt, you notice that it has crystals. And these crystals are either olivine or they're plagioclase feldspar. Olivine or plagioclase feldspar, which are two different types of minerals. And so when we look at the presence of these minerals, we can refer back to something that's called Bowen's reaction series. And Bowen's reaction series tells us specific temperatures of when minerals crystallize out of magma. So you'll notice olivine is on the bottom, and also calcium-rich plagioclase. These are crystallizing at a temperature of about 400 degrees Celsius. So this is confirming what Bingman is suggesting, is that this magma is coming from really deep below the surface and crystallizing during these fissure eruptions. Now, the other neat thing that Carl has done is he's isotopically dated these crystals. So he's age dated the olivine and plagioclase feldspar. And when he does that, he comes up of an age of 2 years old. So the crystals are 2 years old. So remember what I told you is that the Iceland Met Office started to see some ground displacement and earthquake activity in 2019. So this kind of gives us a clue as to how long it's taking for those subsurface reservoirs to infill. So it is at least taking at least 2 years for those dike systems to infill, and we confirm that with the presence of these olivine crystals that are 2 years old. And that's really important because we're looking at a system that we've called unpredictable, but what we recognize is that people are living in this area. So we want to give them some hope and some clue as to what comes next. And maybe not just for Grindavik, but other parts of the island that have this similar type of situation. And so that brings us to the idea, what's going to come next for the city of Grindavik? They're currently evacuated because the Met Office says that another eruption is imminent. But what the government has started to do is they have started to give fair market value to the houses of the people of Grindavik. So the government is starting to pay them fair market value for those houses, and it's suspected that they're just going to pick up the entire city and rebuild it somewhere else, remembering that this is a fishing village. So the question, will they rebuild on the Rainies Peninsula? Remember, there's 6 other fissures on the Rainies Peninsula. Will they build on the southern coast? Perhaps. But remember, when we're talking about the island of Iceland, there's still 33 active volcanoes. So you're never quite far enough away from any type of volcanic activity. But I think the idea that the government is willing to replace their houses and replace the city is a tribute for how much they care about their people. And I think that we can appreciate that and use that as an example for other natural disasters and rebuilding in our country. So I'm happy to answer your questions, comments, or hear your short stories. If you didn't get enough of me, I'm a feature host on the Weather Channel, so you can look for me on the Earth Unlocked. And if you would love to go to Iceland with me, I would love to take you. Thank you.
Okay, thank you. Questions?
Great talk, thank you. So you say there are these 2 scenarios. Could you compare the Hawaiian Islands with Iceland? Are the Hawaiian Islands the scenario 2 all along a fissure, or does Hawaii have both types?
Hawaiian Islands don't have a divergent plate boundary, but they have a hot spot, so there are some similarities. You can certainly get expansion cracks in Hawaii as you have magma that's coming up to the surface. Yeah.
Next.
Those expansion cracks are in proximity of a central volcano. Yeah.
So the plate boundary and the hot spot are coincident. Is that happenstantial, or is there some good reason for that, and will it continue into the future?
Yeah, so the hot spot is stationary, but the plates are moving over top of it. So in the future, way in the future, yeah, the hot spot probably will not be underneath Iceland. But the hotspot itself, I suppose, is happenstantial. Not a lot is really understood about hotspots. There's more than 90 different hotspots on the planet, and there's a lot of randomness to them. They're pretty interesting. They act as buoyant convection cells. So you have these localized bodies of magma that are upwelling, and they're density-driven systems. It takes them a very long time to burn out, to the tune of like 100 million years. But a lot of the randomness of them hasn't quite been figured out yet, like why in some positions you have them and why other places you don't. Because you can have them underneath continental crust, like Yellowstone, or you can have them in the middle of the ocean, like Hawaiian Islands or Iceland.
You showed us the really desolate landscapes, and so I have a question about vegetation. I know you're not a botanist, but can you talk about, on our time scales, let's say 50 years, how much the landscape has recovered, whether it's just lichen or beginnings of plants, or even it just takes longer and it's just a moonscape?
So again, there is a volcanic event every 5 years in Iceland, and some of those are producing volcanic ash. So anything that grows potentially will get covered with volcanic ash that usually has a high acidity, so that kills it instantly. The vegetation, however, is different between the southern coast and northern coast. So once you round the eastern seaboard, temperatures get a little bit colder, but it's a little bit drier. So there's a drastic change in what you see. And in addition, on the southern coast, there's always a continual breeze. So it makes it a little bit hard for vegetation and things like soil to take hold. And that's the bigger kicker, is that there just isn't a whole lot of soil. Now, when the Vikings established themselves in 874, there were trees, but they used those trees. And the city is going through, or the country is going through an effort to replant some of those trees now. The joke in Iceland is, if you get lost in a forest, you stand up. But there's certainly things like birches in a little bit more in the interior where they're starting to take hold by Thingvellir.
Next question.
On the back.
A quick question about the energy source that a lot of Icelandic people use. I'm assuming that the position of those power stations is heavily dependent on what people like you tell, and maybe they need to be moved, though, periodically. Is that the case?
Well, they're really worried about the hydrothermal plant in the Sarvasangeti as of now. They haven't had to. The very first power plant I talked about was Kraftlin. That was opened in 1975, and it's been fully operational ever since. But certainly there is a threat to that hydrothermal power plant, and maybe they will have to move it. But that's the idea is there's high energy fields and low energy fields, high temperature fields and low temperature fields, and the closer you are to the hot spot, the hotter the temperatures, but also the more energy that you produce. So it's kind of you're kind of chasing your tail as far as efficiency.
When Mount Pinatubo erupted, I lived in Jackson, Mississippi, and we had a really pleasant summer. It was much cooler than usual. Is that just due to particulate matter, or that's what I thought it was, but you indicated something else that caused cooling?
Yeah, it certainly could be particulate matter. In the case of Lac eruptions, it was a lot of volcanic gases. And what I should say here is that you can have volcanic events that do encourage greenhouse warming, right? Because you are bringing a lot of carbon dioxide. So I think it is location dependent and event dependent too. Yeah, it can be particulate. Yeah, Mount St. Helens is another example for that. So in Mount St. Helens, 1980, temperature globally decreased about 2 degrees for about a year.
Okay. Next question. Don't be shy. I can see you thinking. Anybody else? Okay. Well, thank you very much.
Thank you for
We really
having me.
appreciate you coming out. Thank you for the show and tell as well with the rocks. They were really nice. All right. So we are going to have these links in the follow-up email for the event. So we'll have that all out for you. So once again, thank you to Manuel's for letting us for hosting us here, even though we were going a little early, but I think that worked out quite well. Did that actually not start? Okay. We're doing all the way again. 1 second. All right. So our next Science Junction in September will be about crypto mining impacts and the future. So it's going to be a panel discussion with at least 2 data scientists and engineering scientists, looking with energy usage and stuff in the state of Georgia, particularly like some of the data mining concerns that are coming in to build data centers where they are doing crypto mining. One of the fun parts about that is that we were just doing some research on energy in Georgia, and the new Plant Vogel reactor that is being started up can support 12 data centers or some sort of like 2 million homes, but not both. So those are the things we're going to be running into. Okay, and if you'd like to be a part of Science for Georgia and help us out volunteering or sharing your knowledge, we do have our monthly membership meeting the second Thursday of every month. And we can only do this through the support of people like you. Thank you for coming out. Here's another scan if you'd like to join us with anything else, especially for our upcoming events like the Science Comedy Show at TELUS on September 13th or our Cancer Charity Show on October 24th. All right, thank you very much and enjoy the rest of your night.